Yeah. I think. Yeah. So before I start, if you have any question. Okay. So so today I'll discuss basically how, as you have seen, that when you integrate out and UV theory, you basically get these effective operators, right? So now we have this low energy theory, which consists of the renormalizable part as well as the effective part, right? And then we have also noted that whether we talk about the bottom-up approach, there also to start with, we add those effective operators. So in both methods, we end up with writing the effective action where you have the renormalizable part as well as the effective part. And with that effective Lagrangian, what we do actually, then for example, in the context of standard model effective field theory that we are discussing, and which is our prior of our discussion rather, right? And then we invoke the symmetry breaking. Once we invoke the symmetry breaking, so then we see that, okay, so whatever we have computed with renormalizable standard model, that means including the operators having mass dimension up to 4, and then we have calculated the spectrum, the vertices, and other observables. And then we want to see that, okay, so if we have added these additional operators, then we expect the spectrum, the coupling, and all other observables to be affected. Because if you see why the observables will be different than the previous one, because observables, if you calculate, they are basically kind of a cross section you are calculating, right? And or some kind of quantity you are calculating out of the cross section. So then the cross section, if you remember, just think of in terms of Feynman diagram. So there consists of basically your vertex factors, okay, and the wave function of the asymptotic states, and the the propagators, the mass and all those things. Now all these individuals are basically changed actually. So we would expect there's additional contribution will show up in our while computing the observables. And what kind of dependence we should expect? That, okay, we are working at dimension 6, okay? So then dimension 6 is basically, if you think the operators are added in the Lagrangian as a C by lambda square, it's a linear in time Wilson coefficient and 1 by lambda square dependence. Now, even if you try to recall the previous part where you calculate the spectrum, that if you add the operators up to dimension 6, then we would say that, okay, all the corrections we would include up to dimension 6, because that will eventually generate some more corrections, which will be order of 1 by lambda to the 4 or more. And that we are not interested in, because we want to truncate our series on the Lagrangian, especially 1 by lambda square. Okay, so we'll be interested to see only the contribution of 1 by lambda square. So then the vertex factor, when you include standard model 1, this is independent of lambda, okay, and then the addition contribution is 1 by lambda square. So now when you add, that is the modified vertex factors in the scattering will also contribute beyond 1 by lambda square, and we will not include them. Of course, we will include them if we think beyond dimension 6, but just to demonstrate you, okay, we are restricting ourselves to dimension 6. Okay, so now all the 1 by lambda square are actually accompanied by Wilson coefficient, which I am calling C. So you should not expect any contribution which is proportional to C square here, because if it is C square, then automatically that contribution will go beyond dimension 6. So with dimension 6 Lagrangian, if I compute anything up to dimension 6, that will be linear in dimension 6 Wilson coefficient C. And that's how actually you can validate your calculation, and you know which of the terms you should throw up after the computation. Now let's, after calculating this modified spectrum in yesterday's lecture, let's try to see what are the different first low energy observers we will be interested in and how they got modified. So first, we go back to our old friend, this Fermi constant. So as you have seen many times now, that this Fermi constant through the matching with the standard model and the low energy effective for Fermi theory, we get the GF at the tree level, right? So this is the tree level matching. And then what we can do actually along with the standard, if you have a universal standard model at the tree level, you have this term. So now what we are doing, we are adding the effective operators with the renormalized Lagrangian, for example, psi square, phi square d. Or then if we have I to getting the wave, so basically you can see this actually generates this psi square d contribution. Now what is psi square d? Now if you unfold this psi d, you will get the gauge field out of that, right? So that will give you some kind of corrections to the current. So that's why the modified current when you include with the psi bar gamma mu psi, the additional conclusion I am showing here as a blob. So this blob actually signifies the presence of an effective operator. So in the standard model level, if it's a G, then this will be G plus some C times C by lambda square. And similarly, the another vertex is basically mimicking the earlier one. So this will be modified in the very same manner. Okay. And then your gauge boson masses, they are also modified. You have the modified spectrum from previous thing. And then you recalculate this process. And once you recalculate this process, then you'll find out this is the some G plus C by lambda square. This is G plus C by lambda square. And the cross term, you'll get some C by lambda square linear. And there's another term C square by lambda square 4. As I was telling you guys that we'll be interested in the dimension 6 contribution only. So we'll throw this C square by lambda square 4 term and we'll calculate the correction of this amplitude up to C by lambda square. So this is one way to get the additional contribution to GM. But that's not the all, because we have the psi 4 operator. And what is the psi 4 operator? Psi 4 operator actually mimics the 4 Fermi operator, but it's a new one. This is written in the standard model effective field theory. That's why you have a direct contribution to the Fermi constant like this. So these corrections should be proportional to some C by, this C 5 corresponding to psi 4 by lambda square, right? So if you do all this manipulation, and then we'll find out that this eventually gives us the correction of this particular form. So now you can see when you add this standard model effective operator, these two operators actually modify your Fermi constant. So now if you know, as you have measured Fermi constant very, very precisely to the measurement of gauge coupling and gauge boson masses, so you can put really constant on these two operators and the lambda. Okay, so this is one of the observables which got modified in terms of the the dimension 6 operators. But also you have to remember in the dimension 6 level, this is the tree level modification. Okay, so you can invoke some further higher order corrections, which is also linear in C, and that will be that then it becomes more and more precise and so on. But this is one of the example to tell you how this the quantities that we have computed already in the standard model context, how that got modified in presence of the standard model effective field theory. Okay, yeah. So any question? Okay. So then let's talk about the weak mixing angle. So one of the way to calculate the weak mixing angle, what I was telling you guys yesterday, that you calculate the spectrum of gauge boson masses. Okay, you put a primary focus on the neutral sector, which is basically your B mu and W mu 3, and then you basically diagonalize that quantity. And if you diagonalize that quantity from there, from this diagonalization matrix, okay, that mixing angle is between the Weinberg angle. Okay, that's one way to calculate the Weinberg angle. But one can measure the Weinberg angle not looking to the spectrum, but through the cross section. For example, if you look at the low energy neutrino nucleon scattering experiment, there you can have this charge current and a neutral current, okay, with the neutrino. And if you calculate the cross section, there you can define your R hat, which is defined in this particular form. This is tells you that neutral current through the neutrino and the anti-neutrino, and that ratio goes with the same as the charge current. Okay, and that is defined as a half minus sin square W. So this relation is exact when you talk about the standard model renormalizable part. But now this charge current and neutral current are written in this particular form, right? So now if you include the dimension 6 operators, what happens that these quantities your spectrums are basically modified. So if you remember this part, that these currents are being modified also along with the couplings and the masses, right? So that's what, when you add, let's say, psi square phi square t kind of operator, which will give you a current J mu mu term, and that will modify this current, charge current, and similarly the neutral current. So you have to encompass their contribution. Now, once you do that, then this sigma and all these are getting modified through these correction terms. And then that will deviate basically from this relation. And if you successfully being able to calculate all those terms in the contrast tandem wall effective field theory, then you'll find out that this is actually the similar functional form, but this theta w is basically not exactly similar as the older theta w, but it's a modified one. And this is my modified with mixing angle. And all the corrections in this in the level of c by lambda square, they are dumped in this theta w bar. Okay, so that's how you can recalculate the modified weak mixing angle. And now you can say, okay, the measured value is not the theta w, but actually this one. And from there, if you fit, and then you see that there's a new kind of operators are appearing which were absent in the GF calculations. Okay, so that's why to capture the effect of other operators to the Weinberg angle, and this is the one way to look into that thing. So this way, actually, you can calculate all the spectrums and the couplings and the observables. And generally, when you talk about the electric quiescent data, then there's a different input parameter schemes are being used. But what I'll be giving the idea about the one of the parameter scheme where you consider this alpha and the GF and the MZ. Okay, the other three-level calculations are included. Okay, and then they are being modified in this particular format. If you input the three-level contribution from them. Okay, and then on top of them, what you can add basically the Higgs signal strength, and this is basically the three-level contributions to the decay width and the production cross sections. What you can compute, and then results are given some literature in a SLH basis. But as you know that how from the previous few slides in the last lecture, when you talk about the how these two different bases of operators SLH and the Warsaw, they are related to each other by the equation of motion. So what you can do, actually, you can translate that Higgs calculations. Either you can talk about the differential cross sections or in fact, the total cross section from one basis to another basis. Okay, but these all will be linear in c by lambda square. Now, here's one important point is basically, if you want to have a much more robust analysis, it is suggested that you better use the differential cross section. The reason is basically, if you use the total cross section, then you are performing the integral over the whole solid angles, right? And then the angular distribution, the angular dependence, and those informations will be lost. So that's why it's better to use the differential cross section, and you have lots of data coming from the CMS and the Atlas. Okay, and that you can use, and then you can constrain those this new Wilson coefficients coming in the picture. Okay, so now let me tell you that, okay, so though we have 59 operators, but not all of them are actually really contributing in this particular case. So when you perform the analysis, you have to be careful, or you have to be at least familiar with, okay, what are the operators that you have to include. So that's what the classification is being done here. So that if you can see, there are 12 operators here which are actually contributing in the electric quiescent data, and the Higgs data, if you include, they are not completely independent of this electric quiescent data. Okay, there are some additional operators which contribute in the Higgs observables, but all these electric quiescent observables also participate in the Higgs observables, right? So that's why once you include the Higgs related data, then you are basically extending this operator set. And interestingly, the electric quiescent data and Higgs data, they are independent. They're coming from two different experiments. One is from left, one is from the LHC, but they share the common set of operators. So, I mean, it is suggested that whenever possible, if you have more data from different kind of experiments, okay, you include more and more, and that will help you to constrain this kind of extended theories in a much more robust way. Okay, so this is the flowchart of how this starting from a theory or in a model independent way, how we can fit the data and what is our conclusive remark. So let's start with from the top down one. So if you start with a top down approach, you must have some preferred BSM theory or some scenarios. Okay, and then you can integrate out those heavy modes. So you get basically an effective Lagrangian, which is part of the SMET. Okay, and then from there, the way we have noted the operators you include, and then basically what to say, the spectrum, the Bartes factors are modified. Then you calculate the amplitudes, and then you consider how they are being modified. Okay, from there you calculate the observers. Okay, and here you can see coming from top-down approach, though the observers are different, but you have to remember the observers are function of the Wilson coefficients. Okay, but these Wilson coefficients are not independent completely. They are theoretically related to each other, and they are function of some model parameters. So that's why in the top-down approach, it is suggested that if possible, you should not restrict yourself to dimension 6. You may go beyond dimension 6 and include more and more observers so that it can take on board more and more operators. Because the number of operators when you include more, it will be more precise, but you are not losing anything by constantly that increasing the number of operators in the top-down approach. The reason is very simple, because for example, if you have two BSM parameters and all the Wilson coefficients are function of these two BSM parameters, right? So now if you have 10 operators, that will be function of two parameters. So eventually this, if you think this observable is function of two parameters only. But now if you calculate these observers more precisely, and then so, okay, there are some additional contributions from 5 more other operators. Those 5 operators are also function of those two parameters. So eventually you are taking conclusion from 15 operators without, paying in terms of the degrees of freedom in the language of fitting. So that's why in the top-down approach, we try to calculate the observers more and more precisely in a realistic way. Okay, and you have to remember this is quite obvious, because top-down approach effective field theory is nothing but replicating the full theory calculation in a very effective way. So if you calculate more and more higher terms and more precision thing, that means basically, though in an effective field theory language you are computing in a particular way, but actually you are getting almost all the contributions that one full theory should have given you, right? Right. So now, once we have the observers, then you find that, okay, so you perform the fitting. But before going to the fitting, let me discuss the another approach, which is the model independent one. And certainly it's a bottom-up approach. So as you know, in a bottom-up approach, you basically add the effective operators, and these effective operators are actually independent from each other, and you do not know their origin. So you treat them in the same footing, so you cannot discriminate them, whether it's a tree generated or loop generated or two loop generated and so on. So you treat them in the same footing, they're independent. Okay, so that's how in the model independent case, when you add the same number of operators that you have done for the top-down case, then you are paying huge amount of price in terms of the degrees of freedom. Because if you have added a 15 operators here, actually you perform the fitting in terms of 15. So that's why one has to be very careful to manage the dealing with the observers and the operator correspondence in a top-down approach and the model independent approach. Now, the question is really, once we write down all the observers in terms of the Wilson coefficients, after that, is there any similarity, or is it a completely different kind of fitting methodology you have to adapt for the top down and bottom up? One has to adapt a different way. The reason is basically in the top down approach, the observers, though you have written down in terms of the Wilson coefficients, but actually they are function of the model parameters. So, and these dependence of the model parameters are completely non-linear. Okay, in the Wilson coefficients that you have seen earlier on the vector like fermion integrated out of the two-dimensional model integrating out. Now, if it is so, then if you perform any kind of a Monte Carlo in the Wilson coefficient plane, that you cannot map directly into the in a consistent way to the model parameter space. So in the top-down approach, it is not suggested that you perform the fitting in terms of the Wilson coefficient. Rather, what you do, you have the observers written in terms of Wilson coefficients, and the Wilson coefficient is a function of model parameters. So eventually, my observers are function of model parameters. You perform the fitting in terms of the model parameters. Okay, you are actually playing with the correct number of degrees of freedom. Then once you have the fitted data for the BSM parameters, then you can use the analytic relations that we have in terms of the Wilson coefficients and the model parameters, and then you can translate the model parameters in the Wilson coefficient space, and there you get the correlations and the allowed regime of the Wilson coefficient fitted for this particular model. Okay, but in a model independent approach, there is no such room for the any other parameter than the Wilson coefficient. Okay, that's why you apart from the fitting in terms of them. So now, to understand the impact of individual operators, what we generally do, we identify one operator we are going to fit, and then we allow all the parameters to vary in a wide allowed range, in a consistent range. And that's why this is something called doing the marginalizations over the all other parameters. Okay, and that's why you will see mostly that you are giving the fitted value for one this thing, one Wilson coefficient, or sometimes you choose some of the set of operators. For example, I focus on the bosonic set of operators and I consider only the bosonic operators, and then try to see the correlations and all those things. And it will be not, and we'll see that in this game, a lot of things that will go inside. For example, just it doesn't mean that if something appearing in an analytic expression of the observers are that your observers will be sensitive to that. Because when you calculate the observers, it also depends on what are the pre-numerical factors before them. For example, if there is some operators whose prefactor is 10 to the minus 5, and there's another operator whose prefactor is 10 to the power minus 2 or 10 to the minus 1, then you know that sensitivity of these two operators will be completely different to these observers. Sometimes you have to be careful, because when you calculate the chi-square or perform the goodness of fit test, you have to be sure that what are the actual degrees of freedom. And why I'm stressing this, because there are a lot of parameters, okay, specifically in the top-down approach, there are a lot of parameters are floating inside your observers, okay, which where the observers are not sensitive to them. They are called the flat directions. Okay, so one has to be careful to identify them first, and then set them to be 0, and then that should be removed from as a degrees of freedom, and then you identify what are the sensitive parameters, and then you perform the fitting, and that's what you can calculate your chi-square and all those things in a much more robust and a consistent way. Okay, so this is how the whole game of starting from the effective, once you have the effective operators and against the data, you perform the fitting, whether it's a top-down or bottom-up approach, and that's how you basically perform the analysis. Okay, yeah. Up to this part, any question? Okay, so we hopefully get the basic idea of how this analysis are being carried on. So now let's see some examples. So for example, there are some 11 scenarios are taken into considerations. Why multiple? Because as I told you, that the reason behind this top-down approach is one of the important aspects is that if you see this standard extension of the scalar fields, their quantum numbers are different from each other. So if I write down a Lagrangian where the standard model is extended by this field or this field and this field or this field, right, or the leptoquark, there is no way to say that, okay, their interactions, their quantum numbers are different from each other. So against the data, I do not know that, okay, whether that data is favored to this guy or this guy, right? So that means basically it will be a wise principle that if we can bring all these scenarios, BSM scenarios on the same platform, And what is the platform here? My similar platform is basically the standard model effective field theory, where my I have degree of freedom and the symmetries are exactly same. And then if we can write down all the UV theories in terms of some standard model effective field theory, then we are ready to perform the comparative analysis among them, right? And that's the basically the primary goal to do that. So now, if you see the tick marks are basically saying that, okay, this operator is generated. At this point, we are not worried whether the T level or one loop level because we are performing the answers up to one loop. So they are generated at the T level, if not T level, but in the one loop. And cross means up to one loop, this operator is not generated. Okay. Now, that is how we made our program used in this particular context and then identify this whole table. Once we have all the Wilson coefficients after integrating out these 11 scenarios, then what we do, we get this one. Now you can see all these operators are written here. Now it is very interesting to see that not all the operators belong to all the scenarios. For example, if you think that, okay, so these operators, right? So these 9 operators, okay, so they are generated whether you integrate out either 2-his doublet or complex triplet or scalar quadruplet. Okay, so any one of them when you integrate out, you basically get many operators, but these 9 operators are basically common among themselves. So now, so that means from the perspective of these 9 operators, these models are basically degenerate. So now look at this real triplet. Real triplet doesn't include these 2 operators. So now anything, any signature which is significantly contributed by these 2 operators, okay, if you observe, then we can say that, okay, see, this model is not giving you these 2 operators up to one loop, right? So that means basically they are less favored compared to these 3 models because they are giving you these operators in the one loop level. Okay. Similarly, if you look at this one, then you'll find out, okay, so these 2 operators are actually, and these 3 are not being generated when you integrate out these 3 models. So all this, clubbing of these models are basically done in a sense that after being integrated out at the SNP level, they are giving you the same operators. Okay, fine. And similarly, the complex singlet gives you only this set of operators. Real singlet gives you these 2 operators, and the others, leptoquarks, give you these 4 operators and so on. So this is basically, it's like a very nice way to present and then display that, okay, which model give you what kind of operators, and based on that, can we club those models? So that's why I call the model degeneracy at this point. So whenever I'm talking about the model degeneracy, one has to be careful. This is not a universal comment. This comment is basically based on the fact that my effective Lagrangian is computed up to one loop, okay, and my observables are, electric equation data and the Higgs data. That's all. If you deform any one of these comments, then of course the conclusive remark might change. You never know that if you calculate the two-loop effective action, then there will be some operator generated from these 2, but not from this one. So that can break the degeneracy. Okay, but we restrict up to the one loop thing. Okay. But this will be discussed again in a another perspective, and that will be more clear there. But I hope at this point also this is clear. But yeah, before proceeding, because this is a convoluted structure we are discussing now. So if you have any query. Okay, fine. So now let's look at the example of this standard modulation by a real singular scalar. So this is the Lagrangian we are talking about. Okay, so why this is Lagrangian, we will not go into that discussion. Okay, so if this is the given Lagrangian, okay, and then if we integrate the singlet scalar, then you basically get these 2 operators, and this is their Wilson coefficient. Now you can see the Wilson coefficient are functions of CSA, kappa S, mu S, and lambda S. All the 4 parameters are there. Okay, but as I was telling you, that you should not be fooled by the analytic expression of the Wilson coefficient and while performing the data, one is very careful. So that's what we did actually. Before going into the actual analysis, we have numerically from the doing the Monte Carlo and varying those parameters and so on. We try to find out what are the insensitive parameters here, and there we found out, okay, this mu s and lambda s, they are basically insensitive parameters. Okay, that means basically whatever be the value of mu s and lambda s, that will not affect the quality of the fit of these parameters. Okay, and they are becoming flat directions. So that's why in this performance analysis, you better set them to be 0, and you say, I have a theory with 2 parameters which are sensitive to my observables. And if you perform the fitting, then you basically get, this kind of a, bound on these 2 parameters. Okay. But now, when you perform the fitting, as I'm telling repeatedly, that from the perspective of fitting the data, the bottom-up approach and the top-down approach, they are widely different. Now you will see why and how much these theoretical correlations can play a crucial role here. So when we have the bottom-up approach, we have this CH and CH box, right? They are completely independent. And if you perform the those Higgs and electric equation data, then you get this gray ellipse, which tells you, okay, if you are within, so all these points are allowed there. Okay, this is a model independent approach, and these 2 Wilson coefficients treated independently. But now you say, okay, now I'm a top-down approach. I have this theory, I'm integrating out, I generate these 2 operators. But interestingly, these 2 having the Wilson coefficient related to each other. Okay, and now I'm performing the fitting in terms of model parameters, and that value of the model parameter fitting, I'm translating them in terms of the Wilson coefficient. And then you'll see only this minuscule amount of parameter space is basically consistent with the data. So now you'll get an idea that how overestimated the things are when you do the bottom-up approach, and how stringent constant a theoretical correlation can play. You see the order of the thing. This is like a zoomed in version of this thing. So this ranges from almost minus 0.1 to 0.9 or something like that. But this is of the 10 to minus 3 order. It's a huge, the scale is completely different from each other. That's why one should not use this bottom-up approach fitted data and translate them into constant the model parameters of manipulation theory. To do so, you have to construct your own effective field theory from a top-down approach and use data, because you know that will leave a minuscule amount of this bottom-up result. Okay? Yeah. Any question? I hope I'm audible. I'm not decoupled.
Yes, you're audible. Can you hear me?
Yeah.
Hello?
Yes.
Yes, yes.
Okay. So now,
Fine.
yeah, was there any question?
No, I was just saying you're audible.
Okay, thank you. Now, let's see this for multiple models. Now, why we are considering these models and these models together? Because in the same theoretical idea that if I integrate them, then from the perspective of the observers that we are considering, all these models giving the same set of operators which affect your observers. So from the model space, they are basically degenerate. Now, should that be reflected in the after fitting the data? Yes, but now depending on the pattern of the interactions, because they are giving the same operators, right? But the Wilson coefficient function of BSM parameters, their pattern are different. So you can ask, okay, will that not be enough to break the degeneracy? I mean, let's decide whether this is enough or not. So again, these models, if you consider, they are the model there are 3 model parameters, but they're actually giving you the 9 operators which are sensitive to this data. That in so one case, you perform this 9 operator, you perform the fitting, and then basically you choose any 2D plot marginalizing over other Wilson coefficients, and then see over this 2D plane of these 2 operators as an example. But in principle, we have shown all of them and which you can observe get all the results here. Okay. So there you can see in this gray ellipse, okay, these two operators are basically allowed, okay, with the data. So now, when you consider them individual models and perform the fitting in terms of model parameters and then translate them in terms of the CHB and CH box operator, you get only this minuscule amount of parameter space which is consistent with the data. Now, what is this? Now you zoom. Now, if you zoom, then you can see that this is actually the order of magnitude is order of like 10 to the minus 4, right? And then at this level also, it's very difficult to understand which belongs to which color. And then you further zoom this space, and then you can see that the breaking of degeneracy of these among these scenarios are of the order of 10 to the minus 5. So now you can understand why I was talking that these are degenerate models, because the level of non-degeneracy appearing is a question of a high precision data, and we are far away to achieve that precision in our experiment, right? So from the perspective of the precision that we have and we are going to have in next few decades even, I would say, okay, that cannot break the degeneracy of this thing. So if we rely only on this kind of equation data and the Higgs data, we will be unable to make any robust comment which can break the degeneracy. That means if you have any data excess or whatever you find out in this particular channels, you cannot say with a confidence that okay, this belongs to this model or this model or this model. So that's why now the people are looking for something more important, newly devised observers, okay, and based on which possibly we can discriminate them. And this is another example with the leptoquark kind of model that you have seen, possibly when the LHCb experiments are going on. There are different kind of leptoquark models are coming up, and everybody was thinking that okay, my model is different from theirs. My question is, are they really different? Now you can check yourself. These are basically function of one model parameter, okay, and then they give you the 5 operators which are actually sensitive to these observables. And similarly, you play the same game bottom-up approach. You get this allowed regime, and then the top-down approach for individual models. And now when you zoom in, and then you can see at the which level of degeneracy they show up in the LHC data and the electric vision data. So now it's possibly the good time to rethink that whether we should come up with another model which may fall in here, okay, or we may think of in a differently, and we should use effective field theory as a weapon and try to think at designing a new kind of observers to really understand at which level we can break the degeneracy of this kind of models. Okay, so this is one of the interesting features of the effective field theory, which will actually display the inner soul of the differently looking models. Okay, which is important because data will look into the inner soul, not the outside, structures. Okay. Yeah. So any question up to this part? So now I'm talking about the data and all those things. Let's see that, okay, so which data plays what kind of role here? So that's why I want to see that, okay, the impact of different observables when you talk about the comparison among the parameter space and the Wilson coefficient space. So let's look at the parameter space. So this is the model where the model is extended by another Higgs doublet. And then what you have seen actually, you have these 3 different parameters which are sensitive to the data. And then you just, instead of having a 3D plot, you just see in a 2D plane. Then you see here that if you have all the data you collect, or you focus on, you switch on only the Higgs data, or you switch on only the electric vision data. Okay, and then you will see that this bluish regime is basically, giving the allowed parameter space, which is basically consistent with the electric vision data. That's quite large value, right? But then when you have this Higgs data, that actually squeeze the parameter space, and when you have switched on both the data, then it's actually give you this allowed parameter space. Okay, and similarly, in a different parameters plane, you get a similar kind of idea. So this will give you the hint that, okay, the role of individual observables, okay, at which parameter is constant by which data more and so on. So they are sensitive in all those things because those are important to understand to analyze them further. Okay. And similarly, in the Wilson coefficient plane, you can see that there's a very minuscule amount regime are basically allowed. Okay. And then you can find out that if you look at the electric fission data, still it's allowing, but once you combine with the Higgs data, okay, because Higgs data actually includes more operators, and more operators mean basically not including the degrees of freedom, but including more contribution, keeping the number of parameters to be same. That's why you would expect it's a squeezed actually, because electric fission data, most of the observers are basically, most of the operators at the leading order, I would say, and this is the leading order electric fission data. So they are already encompassed in the Higgs data, and that's why you can see most of the time the Higgs data plays the most dominant role to squeeze the parameter space. Okay, and that's why whether it's the parameter space or the Wilson coefficient space, they are actually giving you the similar kind of idea. Okay. So now the question is basically what we are discussing many times, that okay, so if we integrate out those heavy fields, right, and then what you find out that the operators that you are generating at the matching scale, right? Now, if your matching scale is very large, because the way LSC is giving you the exclusions of the parameters, actually it's pushing the cutoff scale more and more. So earlier it used to be like 800 GB, now 1 TB, now 1.5, 2 TB. Even now it is also we are using the 3 TB and so on, depending on the scenario. Right? Now the question is, if your lambda is being pushed very high, then there's a quite desert regime in the energy scale from the electric scale to the cutoff scale, and whether will not it be wise to consider the RG effect, because if your lambda is very small, you would expect, okay, the RGs are basically may not play a very important role. But when the lambdas are quite large, for example, few TeV, like for example here 3 TeV, then can they play an important role? How much corrections we can get from there? So this is the plot where you can capture the impact of the RGs actually. So in the same model scenario, but now what we are doing, in earlier fitting case, we are ignoring the RG effect, but now we are including the RG. Now, if you see, this bluish part is basically with the RG effect, and then the reddish part was basically without RG effect. So when you perform the RG, actually it gives you different kind of other operators, and then actually you get more and more allowed, and this is in the context of the all data actually, all the data is concerned. So if you include the RG, we have noted it may give you 15 to 20% even increment in the parameter space. Okay, and this is very difficult to say which RG and how, because these are mostly very entangled one, and one has to do a very case by case kind of analysis with this thing. So you can see their impact, in the Wilson coefficient parameter space, or even in the Wilson coefficient space like this. But it's important to understand that, okay, so how these RGs are important, right? And if I get time tomorrow, I'll be talking about some impact from the the dimension 8 operators, and then we'll really find out that RGs are playing important role. But again, one has to be very careful to switch on the RGs. Why? Because see, when we integrate out the operators, we have a clear-cut idea about which operators are generated at one loop and which operators are generated at T level. So now, for the till date, we have the dimension 6 anomalous dimension matrix computed up to one loop. Okay, many groups, including us, are completing this 2-loop anomalous dimension matrix, but it is yet to be done completely. So now, if you have 1-loop anomalous dimension matrix, using that, you can run only those operators which are generated at the T level. This is just nothing to do with the effective field theory. This is the order by order matching from the quantum field theory. If you generate any operator at the 1 loop, you need a 2-loop anomalous dimension matrix to run them down and so on. So when I'm talking about the RG effect are included, we have identified which operators are generated at the T level. We run them down only because 1-loop generated operators have already the 1-loop effect in them. So we need a 2-loop running for that, which is not available yet. So one has to be very, very careful in this thing. And these are the aspects are missing when you perform the bottom-up approach. Because the bottom-up approach, you do not know that operators are generated at 3 level or 1 loop. So basically, you blindly, perform the RG and all those things. If you want to do, then that's not the correct way of doing that thing. That may mislead some of the result. But yeah, so that's why the effective field is a very sensible.
But in
yes,
bottom-up approach, do you need RG?
So what you want to do actually sometimes you start with the bottom-up approach, okay, and then you try to run back to some high scale and then you try to unfold them if you want to do that thing. Okay. Similarly, for example, low energy effective field theory, if you run from low energy effective field theory apart from the fitting, okay, and then you want to see their status at the standard model scale, then you have to do the bottom-up running, right? But that is not the suggestive way to do that thing. This running is always should be top down.
Yes.
Jayita?
Yes.
Actually, when you are just considering this, I mean the EFT operator, I mean when you are considering the one loop generated operator, are you
Up to one, yes.
considering? Yeah, are you considering this that 1/16 pi square factor with the Wilson coefficient, or you just only considering C by lambda square only?
No. So when I'm saying the top-down approach, okay. For example, let me show you the result. If I have just a minute, I can give you one example on immediate note. Yeah. For example, this model, right? So this model, if you see that I have all the Wilson coefficients with the 1/16 pi square. So the value of the Wilson coefficient is not this, but this times 1/16 pi square.
I see. Okay.
Okay.
Yeah.
That was your question, right?
Yeah. Clear. Thank you.
Okay. Yeah. Any other question? Yeah. Fine. So now another important thing that one has to be careful about the theoretical constant. For example, unitarity, vacuum stability, if you're doing the scalar fields and all those things, those kind of bounds. Why? Because this is a nice example that, for example, in a particular one of the case, for example, if you believe the complex triplet, then if you perform the fitting and all those data, then you find out that this is the allowed regime in this model parameter space. But if you invoke this theoretical constant, then many of the chunk of this parameter space are actually ruled out by that. Okay, so that's why it's always a good idea that along with the experimental data, you also impose the theoretical constants, whatever you have in your hand. Okay, and then all together, when you give up the allowed parameter space, that will be more robust and consistent data. So while performing the fitting, after that, you should not forget to adjust that parameter space in the light of the theoretical constants, because sometimes some of the parameter space may be ruled. This is one of the examples. Fine. Now we'll go to BSM classification, but before that, if you have any question. Okay, so now I'll discuss that there are different BSM scenarios. Specifically, I'll focus on the minimal cases where the standard model is extended by a single scalar representations. Okay, and then if we integrate them out, we can construct effective field theory for individual such cases, and then how theoretically in a much more improved way we can make some kind of comment that okay, which models should be discriminated from others. But this is a completely theoretical. And why it's a theoretical? First, we need to know what are the best we can do. Okay, if some models are not theoretically separable, they are unlikely to be separated by the experimental data. Okay, so that's why the best scenario of this model discrimination we'll discuss now. To do so, what we have done, so we include basically these different scalar fields, one at a time. Okay, this is single extensions. Okay, and these are basically color singlets. All are color singlets, and they don't have any color charges. But then there's another extensions you can do where you have these colored scalars. So there are 15 such scenarios we have adapted. And how the quantum numbers we have assigned, these are basically borrowed from the most phenomenological interesting models across our community. Okay. And now, what we can do actually, that okay, so these are basically scenarios, and then we have incorporated the observables, for example, the Higgs observables and the electric vision data, but we are not restricting ourselves to only reading order, but also next to reading order. Now, before you raise a question to discriminately writing electric vision reading order and next to reading order, let me tell you, observables that you measure, they're basically exactly same for electric vision data, whether it's LO or NLO. In NLO case, those observables are measured in a much more precision. That's why more operators contribute. But the set of observables are exactly same. Then how justified is it to write them separately? This is, as I told you earlier, that this analysis we are doing it theoretically. So theoretically, when I'm saying the observables, in a theoretical sense, the observables are nothing but a set of operators. Because they have a different set of operators, I am calling them different observables. But again, from the experimental perspective, they are not different, they are same. So even after making this separation, we cannot discriminate some of the models. We will conclude the experiment cannot. Okay. So now let's try to read the table. What is this table telling you? That okay, there are column wise, all the models are there, and horizontally the operators are there. Cross means this operator is not generated up to one loop. T means these operators generated at the one loop, but actually when you calculate the actual Wilson coefficient, okay, you will include all the Wilson coefficient that you get up to one loop. So this is the leading order contribution we are highlighting, but that doesn't mean that there will be no contribution for this operator at the loop level. But this operator generated at T level, so this is the leading contribution. This operator is not generated at T level for this model, and not also through the heavy propagator loop, but heavy light propagator. That means in the loop you have a heavy singlet scalar and the standard model Higgs. Now you can see that what is the importance of switching on this contribution. If you do not calculate this contribution, you will be missing out the contribution of this operator even at the same order, right? That's why these are so important to include. Similarly, for this model, all these operators are generated to the heavy propagator loop, but there can be some contribution from the heavy light mixing, but this is the leading order we are saying. And then these operators are not generated at T level. And that's how basically you read whole table. Okay, now you can see there are different set of operators we are colored. Okay, and then you can see that all these scenarios actually offer you the same, all the blue colored operators. So from the perspective of this blue colored set, all are degenerate, but not this one, because this doesn't give you these 5 operators. So that's why if you take an this model along with this model, they are not degenerate. Okay, and that's how we have recreated this model. And of course, we have the Wilson coefficient expressions for each and individual operators for each and individual models, which we are not displaying here because it's not useful at this level of analysis. But yeah, before that, if you have any question or problem to read out the table, you can just point me out this thing, because this will be used later. Okay, so now what we are doing, we are
The last table.
Yes.
Sorry.
Yes.
Yeah. Just a little curious about, most of the operators are either tree or heavy, right? Means there are very few HL
No,
entries.
that doesn't, it's a leading contribution. Tree doesn't mean that they do not get contribution from heavy light.
Oh, okay. But since you
This is the
separated
leading order contribution. That's what I'm saying. This is the leading order contribution. But when you calculate, there would be contribution from heavy or heavy light.
no, but they're
But
not something, but
Hmm?
they're not loop contribution, right? The entries
No,
with
T is the T level. This operator, this heavy field integrate in the T level, then this operator automatically generated and this operator. But when you
Yeah.
perform the integrating up to one loop, there will be some additional contribution to the Wilson coefficient of this operator
Okay.
at the one loop also. And when you perform the analysis, you have to include them as well. Just but for the display purpose, to tell you what are the leading contributions
Okay.
of the operator, that's what we are highlighting.
Okay. So you're saying some of this tree level will have HL
Yes,
contribution.
yes, of course. Actually, in most cases, good contributions are there.
Okay.
Okay. Okay. Is there any other question? No other? Okay. So now what we are doing at this very interesting that we're actually taking on board the idea what the optics people does actually. So if you recall in your optics courses that if you have a source of light, let's say, where it have a different kind of frequencies, okay, and then you create one kind of lens or whatever the instrument which is sensitive to different frequencies. And the job of this instrument is such that if you put a screen here, once you put a light consist of all frequencies or different frequencies on that instrument, then the instrument will club different frequencies and then give you the patch of individual frequencies, right? So that means if there's a 4 frequency lights are there initially, you will get 4 sub patches. So we get this. We actually borrowed this idea. So we are using our set of observers or the set of operators or the observers as that particular instrument. Okay, and this is our screen here, and this is our 15 such models. I would not know how do they go along with each other, and we throw them after integrating out their individual effective Lagrangian or the operators. We are passing through this machine. Now, what is this machine is doing? This machine actually is nothing but a set of operators. So now it is actually identifying which models give you exactly same set of operators. And then after identifying it combine those models and then saying this is a single model or a single class of models. That means this set of observers is equally sensitive to all the models within that class. Okay. So that's why if you switch on only this observer, then you'll find out that these 15 models can be cataloged into 5 such classes, and such that these 3 models are basically treated identically same. These 4 leptoquark models are identically same, and these leptoquark and the complex singlet models are identical. Now you can see this very interesting because these guy doesn't have any color chart. They have the color charges. So it was completely unpredicted before doing this analysis that these 2 models can be treated on the same footing by this data. But yes, they are being treated in the same data. They're equally sensitive to this data, whether irrespective of their color chart they have or they do not have. And then the real triplet and the real singlet model, right? And then we are repeating this analysis considering other observables as a machine. For example, if you switch on the Higgs signal strength, now this again you start with you remove this from the memory and you make a new start. You start with again those 15 models. You pass through this machine, and what it does actually, it actually includes it actually creates 6 different classes. Okay, and now you see they are treated, they are clubbed as per their own. Okay, and interestingly, you see that here this observer was treating this model and other 5 models in the same footing, but Higgs signal strength says no, this is somehow different because this and these 5 are on a different footing. So that's how the degeneracy, what was there with respect to this data, this degeneracy is broken in this particular case. Okay. So similarly, you can switch, as I told, though it's the same observables, but from the perspective of a operators, if you include this as a theoretical observable, then it gives different kind of 6 different classes, and of these 15 models. And then you see that this is actually clubbing more models together. And if you have some additional operators which do not belong to any of these observables, but you do not know what are the possible observables could be, so theoretically you define them as some additional observer. And if you use that additional observers, and then you will find out, okay, they are basically clubbed in 4 different classes. So this was the highlight of those different kind of different kind of sensitivity we can find out through using different kind of observer single time. But our point is basically we have different kind of results in a single slot. So why don't we take a cumulative effect of all this data? So that means we switch on in our analysis all the electric equation data up to next to leading order and the Higgs signal strength and some if others. Okay, one by one, and let's see what does it tell you. So now what we are doing actually, we are switching, we have put these machines one by one. So now we start with these 15 models. Now they are passing through this electric equation data. They are taking this way. Now again, not this one, but this one. These are passed through this thing. So either they can have the existing degeneracy, or sometimes the existing degeneracy is broken. For example, this particular case. Then you use next to leading order and pass it through like this. Then you can see that this degeneracy is still there, but this degeneracy among these 5 models are broken into 3 and 2. And if you can design some more observers with respect to the additional operators or baryon number, lepton number thing, then finally those 15 models will look like this. And you can see that still there are cases where you cannot really discriminate them, because all the operators involved in this kind of observables are generated equally by these models. So that's the level of degeneracy you cannot break. And this is the best theoretical degeneracy breaking case you can achieve. But certainly this is much, much away from the experiments, because this breaking also depends on the precisions and all those things. So one has to be now careful. But what I'm saying that this is a theoretical analysis, and this is the best model inversion problem we can do, and we know what should be the possible status theoretically, which will be worse in the experimental context as well. Yeah. Before that, any question? Okay. So this was all about how this phenomenological thing, once you have the effective Lagrangian, how to do that thing, right? So now we'll stop this kind of analysis here, but now we add the third pillar, if you remember. That was if you start from an experimentalist input, which is basically what are the possible excess you have in the from the data, some kind of operators in a model independent way, and then you try to look for what kind of UV theories could explain that data. So how the effective field theory can play that role. So that's what the tracing back from operators to UV models. So in the top down, we're going to UV models to operators, but now from operators to UV model. That's what we try to learn here. So this is how the workflow goes as. So basically you have these observations, which is in terms of the data. Okay, and from there we identify after the fitting that, okay, which are the what are the excess, and those excess are hidden in which operators, and that's what the tells you what is the EFT you are considering. and then from that EFT, you trace back to the UV models. Okay. So this is what we do actually. So you generally find out that, okay, what are the observables showing some kind of anomalous behavior. You identify them and then find out what are the relevant standard effective field theory operators which can explain that anomaly in the data. And then using a simplified scenario, you unfold those operators through the Feynman diagram and use the argument from the symmetry, and you find out what are the minimal extension of the standard model you can have such that you get those operators. And that's what the paving the path to the DSM model building in a minimal way. So what is the meaning of unfolding? The meaning of unfolding is basically the reverse engineering of the top-down approach. In the top-down approach, if you see, you go from right to left. So you have this kind of scattering. This was the heavy propagator, right? And then you integrate out this heavy propagator in the tree level or even in the loop level. And then you find out, okay, so this is the, effective operators, right? And then the effective operators that you are getting, and then actually, so you can say that, okay, from the given UV theory, I generate this effective operator and the Wilson coefficient. But the question is basically, if I have this, then if I want to unfold this thing, okay, then also possibly I can insert the heavy propagator as per my wish, and then you can show, and then, okay, so what are the allowed, scalar in the tree level or one loop or in the fermion propagators we can include and so on. So this is the going from left to right is the called the unfolding. Okay, and this the most important is this unfolding case, and one of the before employing the internal symmetry, the Lorentz symmetry plays a crucial role, because Lorentz symmetry while unfolding tells you that these will be fermion or scalar or gauge bosons, because that's more fundamental. So that's why one has to unfold this thing. Keep remembering the the Lorentz symmetry invariance, and once you have the Lorentz symmetry invariance, then you have this nature of the spin of the particle you identify first, and then the quantum number of that particle, okay, will be identified once you use the internal symmetry. That is the idea.
Sorry,
Yes.
Jaydeep, how do you get the second and fourth diagram by unfolding?
Second and fourth diagram.
Yeah, from this,
Yeah.
from this
Yeah,
effective.
basically, you consider them to be a 3-point vertex, and this 2 3-point vertex you include by
No,
this.
that is okay. That is okay. The next one.
Oh, this one? You are saying the number
No, actually, no,
the more?
no. The other two.
That's what I
What?
mean. This one.
Yeah, these two. What do you
Yeah. Okay.
said about them?
Yeah.
I couldn't follow actually.
Yeah. Okay. Yeah. It's good that you have pointed out. So the thing is basically when this is a X, right? And this X can be abelian and non-abelian. Now, if you see it's abelian, then the X is basically if you F mu, right? Del mu nu minus del nu mu. The linear in gauge field, but it's a non-abelian, then it is actually in the non-abelian field tensor, you have a one term which is linear in gauge field, then another term which is quadratic in gauge field, right? So now when you calculate the x square and we expand, so phi square x square operator gives you terms which are basically quadratic in gauge fields and also quartic in gauge fields.
Okay, so what you trying to say is that, okay, in that case, the phi square x square that you wrote actually, and on the extreme left, okay,
yeah,
these are not and the corresponding diagram that you have, that might be 6-point or 4-point,
yes,
depending on whether x is okay.
Exactly.
Okay.
Yes. Depending on the choice of your x.
Okay, now I got it.
Yeah. So the most ambiguity will occur in case of non-abelian, because abelian is straightforward. Right?
In fact, this can be 5-point as well, right? Because that could be derivative and then
yes, exactly.
Okay.
Yeah. Any other question about this unfolding? If you have at this point. Okay.
The unfolding is okay. Yeah, I'm still
So now, how do we use that thing? So, for example, we are identifying this heavy scalar as a this heavy propagator, right? So now what we are saying that, okay, my UV theory is a basically universal theory. So at the UV theory, we are allowing the operators which have mass dimension up to 4, right? That means basically, if I have a heavy scalar, then what are the possible interaction it can have? That one heavy scalar can couple to a 2 light scalar, or 2 heavy scalar can couple to a light scalar, or 1 heavy scalar can couple to 3 light scalar, or 2 heavy scalar can couple to 2 light scalar, right? So these are the possible interactions the heavy field with the light field you can write down. There are no other way you can write down this thing. So now, once you fix the quantum number of these light fields, now from this vertex need to be invariant under the standard model gauge symmetry. Okay, then automatically the choice of the quantum number of these are fixed actually. So if I say, for example, if you have phi 1, phi 2 are Higgs H or H dagger, then basically your phi 3 becomes this. Okay. So in this way, for all possible renormalizable vertex, you write down and then you identify what are the quantum numbers of the light fields, because that's what you know. And then from the invariance, you fix the quantum number. Now the point is, it's not always guaranteed that this heavy field will have a unique quantum number. For example, here you can see there are 2 different quantum numbers which will be consistent with the invariance given the phi 1, phi 2 quantum number, right? But for example, in this particular case, the quartic case, even if you know the phi 1, phi 2, the phi 3, phi 4 quantum number can be widely different from each other. Okay, and that's why they can have any generic SU2, SU12, and this quantum. The reason is basically, if you see why it is 2, because if the phi 1, phi 2 are actually conjugate to each other, basically any representation and its conjugate gives you a singlet. So irrespective of the quantum number of phi 3 and phi 4, this phi 1 times phi 2 gives you singlet. Now the only thing that phi 3 and phi 4 can be singlet is basically each phi 3 and phi 4 are conjugate to each other. Now if they are conjugate, they can have any quantum number, and that's what it is reflected here. That's why some of the vertex factors will not give you any robust quantum number or very about this quantum this thing, but certainly trilinear or this kind of quantum numbers are basically much more fixed. Okay, but whatever their outcome, you should make that table, and then once you have this table, then you find out, okay, so what are the possible operators are there, and you try to unfold each and individual operator. For example, if I have this operator, H dagger tau I H W mu nu B mu nu. So you have 2 fields and you have 2 gauge fields, for example, let's say, right? And then you say, okay, I'm giving the minimal extension. That means I do not want to extend my standard model by multiple heavy fields, but only one heavy field. And that too, let's say, I need to get a contribution. So at least one propagator need to be heavy. So if I create only one propagator to be heavy, then I find out, okay, these are the possible choice of my heavy fields I can have. Similarly, not on this loop need not to be considered only for the scalar. We can have a fermion loop with the same external state. And then similarly, for the fermion case, you will find out, okay, these are the possible fermion field quantum number, which are basically consistent and this thing. Now, what does it tell you? This tells you that if I write down a Lagrangian with any one of this field and I integrate that out, I will generate this operator. Okay. Similarly, these are the different choices of the heavy fields we can calculate. And this way, if we pick out individual fields, and from there we find out what are the possible choices of heavy fields corresponding to individual operators. Now, how we can take on board multiple operators and how I can minimize, I can actually shorten the choice of these heavy fields. This is one of the examples. For example, if I look into the operators only, this set of operators, then I'll find out, okay, this kind of quantum number I have as a heavy field fermion, okay, I can generate this operator. Fine. But now I say, okay, along with these operators, I want these 2 operators also. Then it says, okay, it cannot be SE12 singlet. That's why the possibility of SE12 singlet is gone. So you have a one-step improvement in the quantum number. Okay. And then we say, okay, we want this operator. Okay. And then we'll say, okay, if I have to have this operator, then this cannot be any arbitrary. This will have only these possible choices. Okay. And then if I say, okay, I need this operator also, then we'll find out that, that these any one of these operators are not sufficient to generate all these operators and this one. To generate this operator, we need any one of them, but also another operator which belongs to this category, which is not restricted. So you need two heavy fermion to generate this operator. Okay. So in this way, using the symmetry guided principle, we can unfold each and individual operator, and then we can interplay among the set of these operators and then see, okay, which are the fields give you which set of operators common. And this is basically consistent. So the analysis you should perform the following way. From the experimentalist point of view, they are giving the fitted data. Okay, let me go back to that chart. Yeah. So from the experiment, they are giving the data, you identify one or two operators, you construct the EFT with these one or two operators, you unfold them, and you find out what are the possible models. For example, let's say there are 5 models. So these 5 models give you these 2 operators, all of them. But now your analysis doesn't stop here. What you have to do now, you have to pick those individual model and you have to integrate out those heavy fields. Okay, and you have to calculate not only these 2 operators, but all the operators emerge up to 1, 2. So then, along with these 2 operators, let's say individual fields, individual models give you some other operators, and those operators will also contribute on other observables. From in maybe those observables where experimentalists have not found out any kind of excess, but you have to remember that channel where there's excess and where there's no excess, they are described by different operators, but those operators are also function of the same parameters. So then you have to perform a complete analysis with the experimental data, what you have, and also the other data. And then you understand the excess that they are getting, how feasible they are, are they consistent with the other data? So that's how using experimentalist input, you can construct your EFT and this kind of analysis, and you can dictate to your experimental colleagues and then say, maybe this data may not be correct, because if this is true, then that should reflect the excess in these channels, because these are the same parameters which affect this data and that data. So in the one case it is showing the excess, the other case is not showing, something is fishy. Or maybe you have to inherit some kind of cancellation in the other observers. So I'm saying that one has to be very careful and one has to be very, very sincere about this kind of analysis. So now, one of the nicest example you can see through this, for example, if I want to unfold this C-heading operator, pi squared x tilde, then you see from our unfolding analysis, we can have we should have at least 2 different kind of heavy fermion. One kind of heavy fermion cannot help you to generate this operator. So these are the psi1, and psi2, psi2, right? And then we do not know what is their quantum number, but we can fix their quantum number. And from there, if we unfold and then see that they will be generating the CP conserving operators, and one of them will give you the CP hiding operators. And that's what the lesson we have learned from a top-down approach. So this complementary method of unfolding is helping you to reach out there what you have, the knowledge that you have already gathered from the top-down. So these are actually consistently, strengthening your EFT analysis. That's why different kind of perspective you should keep open, unfolding, integrating out, and the bottom-up approach. All these 3 together will help you to understand the effective field theory in a much more neat and clean way. Yeah, so this is some other further more examples where psi square phi cube operator you can unfold, and you can see that you can generate through some heavy scalar or heavy fermion, okay, at the 1 loop and 3 level also. Yeah, this is a few more examples for the psi 4 operator, what kind of things are generated. And you can see these are very economical in a minimal. If you restrict yourself to minimal extension, then there will not be many options to choose those quantum numbers of the heavy field. There are very minimal choices are left there actually, right? So yeah, so I think about this part. I should stop here, and now I should welcome the questions.
Thank you, Joydeep. Any questions, comments from the participants? Just regarding this unfolding, yeah. So let's say if I have a effective vertex, okay. If I have a effective operator corresponding to that, there is, let's say, there's some vertex and or some process that we are actually looking at. Okay, and we're trying to actually unfold that in terms of Feynman diagram, consistent with the Lorentz structure, and also perhaps also the gates symmetry of the standard model.
Yeah.
Should it be only Lorentz structure or also some other symmetries? I mean, for example, if
No, so
the symmetry
basically the Lorentz symmetry tells you that's one thing. You start with this, then
Hmm.
Lorentz symmetry you give possible topologies. Okay.
Yeah.
Which one is fermion, which one is scalar, and so on.
Mm-hmm.
Now, to fix the quantum number, standard gauge quantum number, you need to assign the gauge quantum this thing. So, for example, let's say you have this operator for some other theory. Imagine, okay. Still, these are the topologies because Lorentz symmetry is much more fundamental here.
Yeah.
But if I change the quantum number of them outside particles, okay, then the quantum number of these particles will also change. So the gauge quantum number depends on what.
No, the outside particles are all standard model particle, right?
Yeah, now I'm saying that instead of standard model as a low energy theory, if you consider different theory as a low energy theory.
Okay, no, let's consider the standard model low energy theory.
Okay, so then if you know your low energy theory standard model, that means you know the quantum number of these particles.
Yeah, all the external legs I know.
Exactly, and then from their invariance, okay, you fix the quantum number of this. One of the.
So I'm just saying, so we should then use the additional, let's say, gauge symmetry that we have, SU3 curve, to further rule out some of these diagrams, right?
Okay, I know the topology that's there.
Yeah, if you only use Lorentz invariance, then some of these maybe let's say there are 6 diagrams, and then we can try to think if we, because we know that, for example, that
yeah, so if you restrict yourself to the minimal extension, then not of the diagrams will be generated. Yes, but you can go to a non-minimal version where you may generate that diagram actually. But in a minimal way, you will get a subset of this diagram.
Minimal in which sense you are saying? Minimal
standard model extend by a minimal number of particles. One. If
the low energy theory should have that symmetry, first of all, right?
No, I'm saying a minimal extension by how many particles you are adding with the standard model.
Okay.
Because if you add too many particles, then all the diagrams can be generated and all the operators can be generated, right? But then you lose your predictivity. So what I'm saying that how minimally you can extend the standard model, still you can generate that operator. That is the question.
Yeah. So when we unfold using just being consistent with the Lorentz symmetry, we also have to make an assumption about the particle content of the UV theory, right? Yes.
So basically, for example, I'm restricting myself to fermion, spin 1, and spin 0.
Yeah.
But if I include the spin 2, then of course you have more Lorentz structure.
Yeah. Unless we make an assumption of the additional particle content, we cannot unfold.
Absolutely true. Yes.
And then we can try to see whether once we assume the particle content, we have to also assume maybe some representation of them under
particle content in a sense is more robust to the spin of the particles actually. Only the spin.
Oh, we are only okay. You are talking about only the spin and not their representations.
No, only the spin. First, I need to fix what is the spin I am going to allow. Then it
No,
will,
okay, the speed and the number of, let's say how many different type of field we have.
exactly.
Yeah,
And
yeah.
then the internal quantum number fixed by the gauge symmetry.
Hmm.
Yes. Yeah. That is true.
Yeah, so there is a question on slide number 120. Okay.
Slide number 120.
Yeah.
Sorry. Where those? Yeah, this one. Yeah.
So when we are considering that, hello,
Yes, yes, I can hear you.
when you're considering all the constants altogether cumulative effect. So
At this
first
point? At this
yes,
point or this point?
yes. Let's say the third one.
Third one. Okay. So the
Yeah.
actual data you are talking
All
about.
the yeah. So does the order affect? I mean,
No.
if I
Yeah.
first
That's a good question. Yes. No, their order do not affect, because if two models are non-degenerate once under the light of any data, it cannot be degenerate further. Right.
Okay.
So that's why their ordering is not important. Whichever order you see, the end result is basically the same. So you can shuffle the position of the screen, you will get the same result.
Okay.
Is there any other questions? Okay, if not, then let's thanks Joydeep again
Okay.
for
Thank you for your
today's
attention.
lecture. Yeah.
Thanks.
We'll have another lecture and the last lecture of this series tomorrow. Okay. Thank you, Joydeep.